So our next speaker is Dr. Danielle Vlaho. She is an academic associate in the Department of Chemistry at McGill University, and as the lab instructor for the organic chemistry courses, she is interested in the development and implementation of robust and sustainable chemistry experiments that foster scientific curiosity.
All right, just give me a second. I will get this all ready to go. All right, hopefully it's looking okay. Brilliant. Okay, well, I guess I just want to start by, oh dear. All right, there we go. So I just want to start by saying thank you so much to the Green Chemistry Connections team for inviting me to talk today. And also thanks to Bar for that wonderful presentation. I've learned a lot and I'm really excited about some of the things that you brought up. So to jump in, I basically, as the lab coordinator here at McGill, I oversee the curriculum of all of our organic labs, which includes 4 different courses. So we have 2 introductory organic courses that have fairly large enrollment of somewhere between 600 and 700 students per year. And then we also have 2 advanced courses that are specific for chemistry and for biochemistry majors. We are also planning on splitting up our intro courses this fall so that we have specific labs that are for chem and biochem majors only, and that is a bit of a work in progress. So just a little bit about our approach at McGill. We are very proud to have a very strong tradition of green chemistry research in our department. And we also joined the Green Chemistry Commitment in 2023, which makes us extra motivated to highlight green chemistry, especially in our organic labs. Now, like any institution, we face many obstacles. For us, that takes the form of, dealing with really large class sizes and having many, many students to get through our labs. We also generally have all of our students working independently during their time in the lab, where we might normally be able to, save a little bit in terms of reagents and solvent use and things like that. Because everyone's working independently, obviously that scales up quite a bit. We also have, limited resources in terms of we work with a very small team. We also have limited lab space and of course, limited fume hood space, which means we have to get fairly creative with our course design. All right, so a little bit about our philosophy. First and foremost, we want to encourage a new generation of chemists to keep sustainability always top of mind. And to do this, we try to incorporate green chemistry both in theory and in practice. Of course, we want to, incorporate sustainability, in all of the different experiments that we do as much as possible, but we also want to focus on teaching this stuff in theory. So by talking about the 12 principles of green chemistry, by talking about green metrics with our students, introducing them to how to calculate these sorts of things is all, part of the courses that we try to structure. And the way that we kind of do this at McGill is, rather than trying to always start fresh, we look at how we can make iterative improvements to the existing labs we have. Again, from like a sort of accessibility and approachability standpoint, we find that this is something that works for us. Again, because we are working with a small team, it's something that, we can just kind of focus in on specific aspects of different labs that we think, okay, you know what, we could make this a little bit greener. How are we going to do that? And then just kind of working through things in that way. All right, so as I mentioned, we do like to make these iterative improvements. And for us, it's really helpful to always think of the 12 principles as a sort of framework for doing that. I would say that for us, these are the ones that we highlight as being the kind of most relevant for us. And so if we take a moment and just think about our core goals, as I mentioned already, we want to try to weave the threads of green chemistry through our entire organic curriculum and do this sort of idea of incremental change where we focus on improving small issues and kind of work through like that. So to this end, one of the major things we've tried to do is reduce solvent use as much as possible. We've also eliminated the use of chlorinated solvents in our lower level introductory courses. Again, because those class sizes are so huge, we find this really makes quite a large difference. We try to reduce energy usage and water waste wherever we possibly can. We try to limit reagent waste wherever possible by either reducing the excess of reagents used or reducing reaction scale at large. And finally, we try to reuse or recycle, whether that be products, starting materials, consumables, wherever it's feasible to do so. All right, so what I'd like to do is just highlight a few of the different lab experiments we do and some of those small iterative improvements that we've brought in over the last few years. So the first thing I'd like to highlight is our safety and sustainability assignment. This is an assignment done in that very first introductory organic chemistry course. Basically, we provide students with 3 different methods of the bromination of stilbene. The students are tasked with assessing those 3 methods based on safety, sustainability, and cost. So we have them review SDS for each of the substances that are involved in these different methods, and then assess the relative risk of each of those methods. And we also introduce the students right at the very beginning of their sort of chemistry journey to the 12 principles of green chemistry, and also to how they can calculate particular green metrics. The ones that we focus on for this particular assignment are atom economy, percent experimental atom economy, E factor, and effective mass yield. This is an assignment that we actually brought in over COVID because we had to transition to online labs for this course. And I found that it was a really approachable and easy to implement assignment. And it really did get students thinking about sustainability and also just what it takes to actually run a lab, especially on such a large scale. We also brought in a new introductory lab recently. This is a pretty classic idea, which is the isolation and purification of acetylsalicylic acid, just straight from acetaminophen, from aspirin tablets. I apologize, I think it just should say aspirin there. When we originally wanted to do this, the idea was to have a really kind of simple, stress-free introductory lab for our students that really is just an introduction for them to being in a lab space. Which is a new environment for a lot of them. So we wanted to start with something really, really simple, something that might feel kind of relevant to them, but we also wanted to focus on making it, as safe and as green as possible. As I mentioned earlier, one of our biggest issues in terms of limitations is that we don't have fume hood space for every one of those 700 students at all times. And so we try to design a lot of our experiments so that they can safely be done on the bench. And so this was no different here. For this one in particular, when I was looking into different procedures for how we might do this, I saw a lot of really strong bases, really strong acids, chlorinated solvents, which obviously missed the mark. So we just tried our best to kind of develop this in such a way that we could easily do it on the bench. So using ethyl acetate for a liquid-liquid extraction, as well as aqueous sodium bicarb, using water for our recrystallization step, made it really feasible to do this at large scale with all of our students in a nice, safe, and greener way. In the same course, we also have a distillation lab where our students are separating a mixture of 2 unknown components that are supposed to be whiskey flavoring compounds. What we do with this lab that is kind of interesting is we actually take the distillates that our students create at the end of each lab session, we collect them all together, and we actually recycle them for the next semester of labs. So what we do to this end is we take that distillate, we verify the composition of the distillate by GC and whatever other methods we can, and then adjust the composition of those distillates so that we can basically just recycle all of those samples and reuse them all again. At this point, we've basically been using the same bottles of ethyl butyrate and isopropanol and ethyl acetate for multiple years now, which is kind of neat. We also have an extraction lab in this same course. And again, it's one of these unknown separation experiments. This one we designed at McGill, and again, with the idea of having this only on the bench, we needed to choose our compounds really carefully. So first and foremost, based on their safety profile, but also based on their solubility in ethyl acetate, as well as their acidity and basicity, because that's one of the sort of concepts that they're learning in this lab. We also, really wanted to focus on waste prevention. So to do that, we just really limited the scale of this separation. We use 50 milligrams of each of the 3 unknown components, which means that we can keep the solvent usage to a minimum for that extraction process. Moving on to our introductory organic 2 course, we have a few different labs there where we really like to highlight green principles. So the first one I'll mention is the oxidation lab. I was a PhD student here at McGill back in 2010s or so. When I was a TA for this lab, we actually used to do it with chromium, which is decidedly not very green. So when I originally came to work at McGill in 2017, I was glad that we had at least changed the reactants that were used for this reaction. So by that point, we were using bleach and acetic acid to do the oxidation step. So that was kind of one nice iterative improvement. And then from there, we've gone to a microscale process. So rather than using 2.4 mils of our starting material, we've got that down to 0.1 mil. And we've also changed out the acetic acid for sodium hydrogen sulfate to form our active oxidizing agent there as well. We also do a reduction lab in this very same course. So previously, we have changed the substrate for our oxidation lab just this past year. But previously, we were actually going from cyclohexanol to cyclohexanone and then back, which was kind of neat. And one of the things that we did for this particular lab is we would actually take the products, purify them by distillation, and then recycle them back to use in the oxidation lab. Now we just have, lots of cyclohexanol that we can use for whatever else. But it is kind of a nice way to just not really have to worry about putting more into the waste stream with these products, because often we do end up, sending the products for chemical waste. It's nice to find, other alternatives where we're not having to worry about putting these things into the waste stream. For this particular lab, another kind of recent improvement that we've made is traditionally the extraction step was done using dichloromethane, which was easy enough to swap out for ethyl acetate, which is certainly a lot greener. We also have another set of labs which were recently paired. These are our aldol and Wittig labs. So these are kind of two super classic carbon-carbon bond forming reactions. We combine them into one session to really showcase green chemistry. So both of these reactions are done solvent-free. Both of them are done at room temperature. The aldol reaction in particular uses only ethanol and water for purification. The Wittig lab, being a little bit less green, does use a little bit of hexanes. But what we do have the students do for these two labs is calculate the atom economy and the effective mass yield for each of the two processes, and then kind of compare and contrast those two reactions. Kind of other neat upshot of doing this aldol lab is that our products are traditionally used by research labs at McGill for further transformation. So we've got one of our groups working under CJ Lee does a lot of kind of substrate scope investigations, and so the chalcones that our students made in this aldol lab were actually shipped off to the Lee lab so that they could be used in research, which was kind of nice as well. Going up to our advanced labs, just one I'd like to highlight there. This one actually comes to us from U of T. So this is a reaction developed by Andy Dix. It is a Suzuki lab. So this one is nice because it is a nice use of catalysis, so showcasing that for our students. We use a really small amount of palladium for this reaction, but it could be recovered because it is a heterogeneous catalyst. We also don't need to use a ligand for this one. It's nice because this is an example of a Suzuki where we're using water as a solvent instead of something more traditional like dioxane or DMF. In terms of energy efficiency, we used to do this using water condensers and recirculating systems. We've actually removed that entirely. So all of the refluxes that we do in these advanced labs, we actually do using Vigreux condensers, which really you don't need any water at all. So we're not having to worry about recirculators or energy or water use or anything like that, which is quite nice. And again, for this lab in particular, we really highlight the calculation of metrics. So we have our students look at this Suzuki process compared with a more traditional process using more traditional solvents, and then calculate out the metrics just to see how it really does stack up. I'd like to just also take a moment and highlight a couple of the other and more recent initiatives at McGill. So we have recently started recycling the acetone that we produce in our organic labs. And for the last couple of years, at least, we've been recycling our nitrile gloves as well. These are things that the students have been really quite interested in. So it's really nice to see that they too are, concerned about what's going into the waste, how these things are handled. And they're really happy to see that we have, been thinking about that and, coming up with some ways that we can kind of minimize those wastes. I also wanted to just take a brief moment to talk about a couple of things that we are looking towards. As I mentioned, we are currently working on an entire course redesign for our introductory lab curriculum. And so a couple of the reactions that we do there. So we also do an amine synthesis. Here we're using vanillin and benzylamine. One of the particular steps in this lab that we don't really love is that we do a trituration in hexanes, which is not super ideal. We realize that, we can actually just eliminate that purification step entirely. This means that the imine formation step for this reaction is solvent-free, and the following reduction to the amine uses ethanol and water. So overall, other than the fact that we're using benzylamine, it's not too bad. And I think we'll look into changing the substrate for that one as well. And we also do one of those kind of classic column chromatography experiments, which is separation of spinach pigments. Here we have a liquid-liquid extraction step where we isolate the actual pigments from the spinach leaves, and we're looking at how we might be able to still get a really nice, crisp separation, but instead of using that liquid-liquid extraction process, how we might be able to isolate the pigments in a different way. In this particular case, we're looking at grinding up our spinach with magnesium sulfate and sand instead of having to use any solvents at all. So, like I said, just a few of the highlights of various things we've been working on and how we try to use those 12 principles to kind of, inform us as we make these little changes and hopefully make things better every step of the way. And with that, I'd just like to give a big thanks to my colleagues in the Department of Chemistry, specifically Mitch Hewitt, who has been working with me on the organic labs for the last semester, our wonderful technical staff, and our wonderful Student Society Green Chemistry McGill, who also helps out a lot with our acetone recycling and our gloves recycling program, and are very excited about all of the sustainable initiatives around our department. So thank you all so much, and thank you for having me.